we are going to give today a session about functional programming, and the name of the session is A Practical Introduction to Functional Programming. So I'd like, on one hand, to talk about the paradigms of functional programming, the idea behind the functional programming, but most important, I want this session to be really practical, so that it gives you guys tools and tips and tricks to really start using functional programming in your day-to-day job. And if you are already into functional programming, I hope that you will get a deeper understanding of what is functional programming, and maybe have a better understanding of the functional programming paradigms, languages, and how to write proper code in functional programming. So let's start. Our agenda today is going to be in 4 steps. The first part, we will talk about the paradigms of functional programming and how those paradigms apply in functional programming languages like JavaScript, Enclosure, and Ruby. Then we will give a brief history of functional programming, and we'll see that at the beginning it was really a niche domain of software programming, but over the years it has become more and more mainstream, and hopefully in the upcoming years it will become even more mainstream. And we will see also functional programming in practice, how the paradigms of functional programming apply to mainstream technologies and frameworks like React.js, Redux, and also we'll talk a bit about web servers that you can write with functional programming, and if time permits, we'll talk also a bit about big data. And I hope that at the end of part 3, we'll have time to discuss, and if you have questions about functional programming in general or in practice, I hope that we could have a pleasant discussion together. So my goal today is really to give you a test of functional programming, hopefully a good test. And after you have tested functional programming, you will be completely motivated to try functional programming at work, either to try a language that you have not tried already, or to go deeper in a functional programming language that you already know. A word about myself. My name is Jonathan Charvit. You can find me on Twitter with my handle Viebel. I'm a mathematician and a coder. So it makes me something that I call a pragmatic theorist. I love theory, but I love theory when it is pragmatic. I don't love theory for the sake of itself. I love theory for its applications. And as you will see in the presentation, I am a freak of interactivity, of code interactivity. You will learn more about it during the presentation. Back in 2013, I founded a startup in the domain of web audiology, and we were proud to have 30,000 lines of ClojureScript code, which is pretty decent for a ClojureScript front-end application. And I am also the author of a nice library named Clips. It's a JavaScript plugin that you can plug into any web page, and it will transform code snippets into snippets that are interactive and you can evaluate in the browser. And actually, I'm going to use Clips inside this presentation. So if you like it, feel free to give Clips a star on GitHub. Today, I work as a web consultant, a full-stack web consultant in the following technologies: Clojure, ClojureScript, Ruby, Ruby on Rails, JavaScript, and React. And you can hire me on Codementor either for a project or if you want a one-on-one session of 1 hour or more in one of those languages, I'd be happy to help. So what are the paradigms of functional programming? And what is really the definition of functional programming? So it's hard to give a precise definition that everybody will agree on it. But basically, the definition of functional programming is a language where functions are first-class citizens. It means that you can manipulate function almost like you manipulate numbers or strings, arrays, etc. So for instance, in Java or C++, objects are first-class citizens, but functions are not first-class citizens. When you want to manipulate a function or to pass a function to another function, you have to wrap it into an object. So usually in object-oriented languages, objects are first-class citizens, and in functional programming languages, functions are first-class citizens, and we will see that there are languages that are both object-oriented and functional programming languages. And once we have this definition, we can continue with the paradigms of functional programming. So usually in functional programming, we prefer declarative style instead of imperative style. And we prefer to have pure functions, meaning function with no side effects, and function that does not depend too much on global variables. Also in functional programming, we prefer immutability. So we don't mutate objects in place, but we create new versions of the objects, making our objects immutable. And another paradigm that appears often in functional programming is the concept of laziness. Now we are going to deep dive into all those paradigms. So what does it mean to be a first-class citizen in a language? It means, and what does it mean for a function to be a first-class citizen? It means that functions can be passed to variable definition. So you can define a variable A to be a function. Also, you can pass functions as arguments to other functions. And even you can write functions that return functions. So let's see it in action. Okay, now it's time for you guys to join me and to either scan this QR code or go into this link, and then you will be able to, I will send the link also in the chat. So here is the link, and then you will be able to follow the slides along with me. And it's important because you will see that the slides feature many code examples that are interactive. So you guys will be able to manipulate and interact with the code that I'm presenting. And instead of asking what happens if instead of A, I'm using B, you can just try it by yourself. And I hope that you will enjoy and that you will find it effective for your learning experience. So if you're ready to climb, join the link, scan the QR code, and bear with me. Okay, so let's see, for example, in JavaScript, you guys are probably familiar with JavaScript. There are two ways to define a function. This is the standard way with the function definition. So this is something that resembles what we have in non-functional programming languages like C. But also you can define a function like this without giving it a name. So here you have a function, and then you can define a variable with var, bar, and the variable will hold the function. And as you can see, foo and bar both work. It returns 43 on 32. And if you want to play with it, modify a bit the implementation of foo or bar, you can play. If you want bar to receive an argument, and make it x times something, then bar, you can pass whatever you want. So it's fully interactive. Feel free to play, to interact. It's there for you guys. So this is in JavaScript. And in the newer versions of JavaScript, in what we call ECMAScript 6, it's even shorter to define a function. And instead of the function and the curly braces, you can use the arrow notation where you put the function arguments and then an arrow and then the body of the function. So again, if we want a function that receives an argument, we do it like this. If we want more than one argument, we do it like that. Then we can pass the arguments. So here in ECMAScript 6, when you want to define a function, the way you do it is that you first define an anonymous function, and then you pass this anonymous function into a variable. So this is what I meant by when I say that functions are first-class citizens. The first characteristic is that functions can be passed to variable definition. Now let's see how we do this in Clojure. So first, the regular. So in Clojure, I don't know if you guys are familiar with Clojure. We use the, I forgot if it's infix or prefix notation, where we put parentheses. We wrap every expression in parentheses. We will see it more and more. So this is how we define a function in the regular way, like we did here in JavaScript. So here we have a function foo_x that receives no argument and returns 42. But we can do it with an anonymous function also. So here we have an anonymous function that receives no argument and returns 43. And then we pass this anonymous function into a variable definition named backs. And here I have an array that contains the application of foo_x with no arguments and the application of backs. So in Clojure, this is how we apply a function. Instead of having the name and the function and then the parentheses, we first put the parentheses and then the argument. So let's make foo_x receives one argument. Then it will return x multiplied by 42. And then we can pass an argument to foo_x. Okay, so if it's not 100% clear, feel free to ask questions in the chat window and I'll be happy to give more details. So this was Clojure. Let's see how we can do that. We can define anonymous function and pass it to variable in Ruby. So again, this is the usual way to define function in Ruby. Def, the name of the function, and then the body of the function. So foo_w will return 42. But you can also have lambda or anonymous function in Ruby with the arrow and then parentheses and then the body of the function. There is a subtlety in Ruby. So when you want to apply a regular function, you use parentheses. But when you want to apply a lambda function, you need to use a square bracket. Sometimes it could be cumbersome, but this is the way it is. And again, we can pass an argument and we will call bow with one argument. Okay, so far so good? Okay. So that was the first characteristic of functions being a first-class citizen. When you can pass function definition, you can pass function to variable definition. Now we'll see that you can pass function as arguments to other functions. Let's see it, for example, in JavaScript. We have the map function that works on an array, 1, 2, 3, and we'll apply this function to each element of the array, and it will return another array. So here I have a simple function that adds 1 to x, and as you can see, this will return me an array of 2, 3, and 4. So this is the map function. This is one of the basic building blocks of functional programming. In ECMAScript 6, it's even shorter with the arrow notation, the same. And by the way, when the function receives a single argument, you can omit the parentheses. it works exactly the same. Okay, Enclosure, the functions, so just a second. In JavaScript, the map function is a function of the array object if you want. But in Enclosure, we don't really have objects, so every function is a regular function. So the order is a bit reversed. So we have the map function that will apply the inc function on the array. So inc function is a function that increments. So when we call map with the inc function on the 1, 2, 3 array, we are getting back 2, 3, 4. Now let's see it in Ruby. In Ruby, it resembles a lot what we saw in JavaScript. 1, 2, 3, map. And here is something that is almost a function. It's not really a function, it's a block. There are subtle differences between block and function in Ruby, but basically it's the same idea. You apply a piece of code without a name. So it's an anonymous block, it's kind of an anonymous function. And you apply it to each element of the array. Okay, now something a bit deeper. In functional programming, we could have functions that return functions. And an example of such a function is the partial function. So the formal definition of partial is partial takes a function and a list of arguments and returns a function where some arguments are fixed. So it's a bit cryptic. Let's see it in action. In JavaScript, we don't have a partial as part of the language, but there is a cool library named Lambda that implements partial. So let's define a function add that receives 2 arguments, x and y, and returns the addition of them, so x plus y. Now we are going to make a new function named add10 that is going to be the add function where the first argument, so the x argument, is going to be fixed and to be 10. So this is what we call partial. And now, as you can see, add10 is a function that receives only 1 argument, 19, and it will call add with 10 and 19. So this is what was mentioned in the definition. Some arguments are fixed. The arguments that you pass to partial as fixed into the function returned by partial. Is that clear? Okay. Now in ECMAScript 6, exactly the same with the arrow notation. Again, add10 partial. And again, you can play with it. If you want to fix the x to be instead of 10, 9, you can see it in action in your browser. Enclosure, partial is part of the language. So we'll see how to write it. So again, we have the add function that receives 2 arguments, x and y, and returns the addition x plus y. What is the syntax to fix the second arg? So let's go back to here. You want to fix the y, right? So if you want to fix the y, you just pass it another value. And then add10 now is a function that receives no argument. And x and y has been fixed to this and that value. Make sense? Luke? Oh, if you want to fix y but not x. So you can't really do that. What you can do, let me show you in the Lambda. They have, so if you go to the documentation, they have partial right. So you can decide to fix the arguments from the right, from the last argument and then the one before the last, etc. You cannot decide to fix, let's say you have a function with A, B, C, D, E. You cannot really decide to fix A and C and E. You can either fix A, B, C or E, D, C. So this is partial versus partial right. Okay. So now Enclosure, I don't think that we have partial right, we have only partial. So here we have our function add that receives 2 arguments. And here we are going to define another function that receives, a function add10 where 10 has been fixed. And we call partial add10. And now add10 is a function that receives only 1 argument. There is a difference here. In Lambda, when you want to fix the arguments, you need to pass an array. In Clojure, you just pass the argument as they are. You don't need to wrap them into an array. And again, you can play with the code. And in Ruby, there is something called curry instead of partial, but it works almost the same. So again, here we have a lambda function xy that returns x plus y. Yeah, and also before I mentioned that when you want to apply a lambda function, you need to use square bracket. You can also use dot and then regular parentheses. So here we are going to curry. So we take the add function and we are going to curry with 10. And now add 10 is a function that receives a single argument and applies it to add where x has been fixed to 10. So I hope that you got the idea of a function that returns a function. So let's check that you have understood it well. Let's try to implement our own version of partial. We will make a simple version where we are going to assume that our function receives 2 parameters and we are going to fix 1 parameter. So go for it. Decide in what language you want to use, either ECMAScript 6 in this box, or Clojure in this box, or Ruby in this box. So I'll give you 2 or 3 minutes to try it. And when you are done, just write it on the chat and I will continue. And I will show you my implementation in ECMAScript 6. If you have questions, also you can ask in the chat room. Okay, so let me show you my implementation in ECMAScript 6. So partial is a function that receives a function f and x, and it will return another function that receives 1 argument y, and it will return the application of f in x and y. And as you can see, partial at 10:9 works as expected. Okay, so that was a function that returns function. Okay, so this completes the part about functions being first-class citizens in functional programming languages. Now we will see another characteristic of functional programming, which is that we prefer declarative style. So in order to understand what do I mean by declarative style, let's compare map and for in JavaScript. So when we wrote the code with map, as you can see, we didn't have to deal with the low-level details. We only expressed what to do with each element of the array. Again, if you see it here, this is the array, and this is the function that I want to apply to each element of the array. I don't care exactly how the array is going to be iterated and how the returned array is going to be built. This is hidden into the implementation of map. But when, as a developer, I'm writing code, I want to express only the what and not the how. And it differs a lot with when you compare map with for. So this is the code, the same code for incrementing each element of an array using a for loop. And if you pay attention here, you see that with for, I have to express how the array is going to be iterated from left to right, for example. What is the name of the index that I want to give? Here, I decided to call it I. How I'm going to decide that I'm done, that the array has been completely consumed, and how the elements are going to be combined into the return array. Here, for example, with the push function. So it's a lot of low-level details that in functional programming, we want to get rid of them. At least we don't want those details to appear in our code. We want them to be hidden in a lower layer of abstraction. So that is a key characteristic of functional programming. We want to deal with the what and not too much with the how. Okay. Also, in functional programming, we love pure functions. Oh. Okay. So pure functions. What is a pure function? A pure function is a function that depends only on its parameters and not, or on its argument, and not on the global state. And it's a function that has no side effects. I will explain in a moment what I mean with that. So not all the functional programming language constrain you to use only pure functions. If you go to a very pure functional language like Haskell, I think that there it's very hard to write impure function. But in looser functional languages like Clojure, you can write pure function and impure function. But we encourage you. It's a good practice. It's a good paradigm to write pure function. And we'll see here how to translate an impure function into a pure function. And why do we want to have pure function? Because when we have pure functions are much simpler to combine, to test, to debug, to understand, and to refactor. Sometimes you may think that they are a bit harder to write, but then when you get used to it, it becomes not too hard, and all those characteristics, the combination, the testability, the debugability, the understanding, and the refactoring are really, really important characteristics when you write, when you work on a project with many functions and many, many lines of code. So let's see what does it mean for a function to be pure. So first, an impure function. So this function, the ren, depends on a global parameter n. And you see here in the signature of the function, you cannot really see the dependency of ren, the fact that ren depends on n. So there is an implicit dependency. And when you call ren, you don't specify what is n. And if you change n, and you don't change your code, so here you call the exact same function. By changing the value of n, you can change the implementation of ren. So this is what I mean, that this function is not pure because it depends on the global parameter. So let's see how to rewrite it as a pure function. If you want to rewrite it as a pure function, you need to make the dependency on the n value that I'm calling max here explicit. So max needs to be an argument to the function. And now you can see the dependency, the explicit dependency, and you can, in order to make ren behave differently, you have to modify the code that uses ren. So the first function was not pure because it has implicit dependency or dependency on the global state. And this function is pure because it doesn't depend on the global state. Okay. The second characteristic of pure function is that it has no side effect. So what is a side effect? Side effect is something that is done by the function beside the return value. For example, printing into the console, writing into the database, sending an HTTP request, sending an email, or whatever. So in this simple example, the try something function will return X times 42, provided that x is truthy. And if x is not truthy, it's falsy, it will log into the console. So here I passed nothing, which is undefined, but I could pass also false. And you can see here the side effect. And if I pass a truthy value, you can see the return value of the function. So this function is not pure because it has a side effect. And you can ask yourself how I'm going to test such a function. It's really hard to make sure when you want to test also the error path and the success path. So the success path is really easy to test, but the error path is not so easy to test because you will have to make sure that the console log function has been called. So you probably have to mock the console log, and it brings a lot of complexity into the test. If you want to make this function pure, you will have to rewrite it, for example, in this way, where the try something function now is going to return not only the value, but also the status. For example, you can combine the status and the data into an array. So this is a trick that I like. So if x is true, you will return an array, and the first element of the array will be the status, that it could be either OK or error. And then in the second value of the array, you will pass the data. And in case of a success, the data is going to be x times 42. In case of a failure, the data is going to be a string that explains what is the failure. And if you want to log the result of the failure into the console, you will do it in the function that calls try something, but not inside try something. Okay. Another characteristic of functional programming, another good paradigm is the immutability. What do I mean by, in order to understand immutability, we have first to understand what is mutability and what is the problem with mutations. So in non-functional languages, the default API provided by the language mutates the object. Let's see it in JavaScript. So here I have an object, A. It's an object with one key size, and the value is 42. And here I have B equals A, and look at what happens now. I'm modifying B. So I think that only B is modified, but actually A has been also modified. So see, A was 42, and by modifying B, I was able to modify the value of A. So in this example, it's not hard to understand what happens, but if you think about a real code base with a lot of functions and function that calls function, it could be really complex to understand why A has been modified without me touching A. For example, I could pass A to another function, and this function A is called B, and this function is going to modify B, and I will not understand why in my code, although I didn't modify A directly, A has been modified. So this is the problem with mutation. It makes the code much more difficult to understand. And exactly the same happens with in Ruby. Again, you have A, you put A into B, you modify B, and A has been modified. So in Clojure, we don't encounter this problem because Clojure data structures are immutable. You cannot mutate B directly. So in the next slide, we are going to see how Clojure deals with immutable data structures. Yeah, so what is the solution to the mutability problem? It's the immutability. It means that instead of modifying the object that you have, you create every time you want to modify the object, you create a new version of it and you modify the new version and you leave unaffected the original version of the object. So if you are going to do this by hand, it's going to be not effective because it will take time to clone the object and it will take a lot of space to maintain all the versions of the object. But some languages like Clojure support immutability natively, and they provide a very effective implementation of persistent data structure. So let's see it in action in Clojure. Here I have a variable A, where the size is 42. I put E inside A, and then I'm going to assert. Assert enclosure means modify a key of an object, but it doesn't modify the object in place. Instead, it returns a new object C where the size key has been modified. As you can see here in the output, so this is A, left with 42. This is B, left with 42, and only C has been modified. And it's very interesting that Enclosure, the standard library, does not provide a way to modify the object in place. So it puts a very high constraint, a very strong constraint on the developer to deal with immutability. And you may think that these constraints limit your power of expression, but actually it doesn't limit your power of expression. It makes your code more robust. What about immutability in JavaScript? So immutability is not provided in native JavaScript, but it is provided by some libraries. One of them is Immutable.js. And let's see it in action. So this is the namespace for Immutable.js. In order to manipulate immutable data structure, you have to convert your JavaScript object into an immutable object. And now A is an immutable object. And then when you want to modify part of A, you call set or set in if you want to go to a nested element. So in that case, I'm going to modify the size true to be 43 instead of 42. But as you can see, A remains unaffected, and only B has been modified. So B has choose 43, but A has choose 42. So this is how you achieve immutation in JavaScript. There is also a library that provides immutability for on Ruby. Okay, so far so good. Please give me feedback on the chat that you are with me, that everything is 100% clear before I continue. Okay, I'm going to continue. Laziness. So this is the last important paradigm of functional programming. Lazy sequencing. So what do I mean by lazy? Lazy means that the elements of the sequence are calculated only when you need them. So for example, in Enclosure, let's take again the example that we showed before, where we want to map each element of an array to increment it. And let's add a side effect to the function that manipulates the element of the array. And you will understand in a second why. So lazy A is a lazy sequence. And as you can see for the moment, so just I'm going to show you that if I'm calling print directly here, it will be printed in this snippet. So let's remove it for the moment. So lazy A is a sequence. It has been created, but actually this function has never been called yet. And it is going to be called only when we access the element of the sequence. So here I'm accessing the nth element and the element 0 of the sequence. And in order to access the element 0 of the sequence, I have to apply this function, the mapping function, to the first element of the sequence. And when this function is called with the first element of the sequence, the print will be called. And this is why you see here val1. If I'm going to call to try to access the second element of the sequence, we see that first I have to access the first element and then the second element. And this is why the value is printed twice. But if I'm accessing again, okay, now if I'm accessing again the first element, the value is not printed because the sequence has been cached. So there is no need to recalculate the mapping function. But if I'm redefining, here I'm redefining the lazy sequence, the function will be called again. Yes, and only the first time. So again, redefining the function. First time, the mapping function is called with 1 and 2, and second time it's not called because the function results are cached. Okay, now that we have lazy sequences, we can do amazing things like having infinite lazy sequence. So usually in with regular sequences, with non-lazy sequences, obviously you cannot have infinite sequences because it will much earlier than much before you reach the infinite, you will explode the memory of your computer. But if the sequence is lazy, we don't have such a problem because we don't need to actually calculate the element of the lazy sequence. For example, here it's the range function enclosure that returns all the numbers from 0 to no limit. And we see that it takes no time to create this sequence. And I can take subsequence of this sequence. For example, with the take function, I take the 10 first element of this sequence. So natural numbers, it's an infinite sequence. And I can deal with it. The only thing that I cannot do is to count the element of natural numbers. If I try to count, it will stack the. I will go into an infinite loop that will never exist. So let's see a couple of other examples. We can also repeat. We can also have an infinite repetition of an element with the repeat function. So infinite hello is going to be the repetition of hello in infinite time. And we can take, for example, the nth element. And no matter what number we put here, we will get hello. And if we take, let's say, 5 elements, we see that we have hello repeated 5 times. Okay, we can also, let's keep this example. So now that you have seen what are the paradigms of functional programming, you wonder who created functional programming and what happened with functional programming today. So let's review a brief history of functional programming. So functional programming began in the 30s at the same time that Turing discovered his Turing machine. Another smart guy in the US, Alonzo Church, discovered the lambda calculus. And in lambda calculus, everything is an anonymous function with one argument. There is no names in the language. You cannot name variables. You only have to deal with function arguments. And it's amazing that even numbers can be expressed or encoded as functions. So for example, this is the definition of zero in lambda calculus. So 0 is a function, lambda is a function that receives two elements, f and x, and returns x. 1 is a function that receives f and x and returns the application of f to x. No matter the details, just I mentioned here that all the function has with one argument, and here it seems that the function receives 2 arguments, but actually there is a way to encode function with multiple arguments into function with a single argument. So that was the beginning of functional programming in the 30s. And then there is a gap of 28 years until in 1958, John McCarthy invented Lisp. So in a sense, Lisp is the first functional programming language. And in this language, everything is an S expression. So instead of having 1 plus 2 plus 3 or plus 1 to 3, in Lisp, you wrap the expression and its arguments into an S expression with the parentheses. And the amazing thing about the first version of Lisp is that it had only 7 terms: car, CUDA, atom, lambda, label, cone, and code. And so this is the only terms of the language. And with those 7 terms, John McCarthy was able to demonstrate many nice things in his language. In 1995, JavaScript was designed by Brendan Eich. And it's funny because at the beginning, Netscape recruited him, and they wanted him to do Scheme in the browser. So Scheme is one of the Lisp dialects. And eventually, instead of Scheme, Brendan invented the JavaScript, which is very different than Scheme. But one thing from Scheme remained, it is the fact that in JavaScript, function as first-class citizen. So in a sense, you could say that JavaScript is a functional programming, is a functional language. In 2004, Scala was invented by Martin Odersky. And I think it's the first functional programming language on top of the JVM. So Scala is a JVM statically typed language with functional programming support. Scala is very, very complicated. Clojure is the Scala competitor, and it's much simpler. Yeah, but Clojure appeared only in 2007 by Rich Hickey, and Clojure is Lisp on top of the JVM, but with emphasis of the fact that it's practical. So there are many Lisp dialects: Lisp, Common Lisp, Scheme, Scheme 1, Scheme 2, and whatever. But all those languages are very pure and very coupled with the original idea behind Lisp. Rich Hickey allowed to himself to be a bit more practical. And this is why Clojure was much more adopted than all the other Lisp dialects. In 2011, ClojureScript was released. So ClojureScript is Clojure transpiled into JavaScript. And because JavaScript is everywhere, JavaScript reaches, and Clojure works, it made a lot of sense to have ClojureScript, which is a transpilation of Clojure into JavaScript. And this is how we can have a ClojureScript running in the browser. 2013, Facebook created React.js. So React.js is JavaScript framework for building front end. But the nice thing about React is, as we will see later, it's a functional framework. So many of the paradigms that are presented in this presentation before, you will see that they apply to React.js. And React.js is very, very popular. It's definitely not a niche framework. And 2 years later, in 2015, so just 2 years ago, Dan Abramov invented Redux. And Redux imposes functional programming constraints on the front-end app. So you have constraints on the way you write your application, but we will see that you have also, because of those constraints, you enjoy many benefits. And today, we are here, May 23, a practical introduction to functional programming. Yeah, so functional programming in practice now. In the front end, many functional languages are transpiled into JavaScript. We mentioned Clojure, but there is also Scala.js, and there is F# transpiled into JavaScript, and there is also OCaml, and probably many other languages. One of them, my preferred one, is ClojureScript. And actually, when you saw all the code snippets in the presentation in Clojure, they were powered by ClojureScript. So this is how you can enjoy Clojure in the browser. Okay, now let's talk a bit about React.js, the functional front-end framework. So in React.js, you have two basic insights that imply many guidelines. So the first insight is that the UI of a front-end application could be seen as a pure function of the state. So there is the state of the application with what they call the virtual DOM, and the UI, the real DOM, or what you see into your browser, is just a function of the virtual DOM. So instead of dealing directly with the DOM, you could deal with the virtual DOM if you express the state of your application as a plain JavaScript object. And instead of composing the HTML or the DOM, in React, we are going to compose using functions, because functions compose very well. So here are the guidelines in React. You write functions that create UI components. the state is expressed as a plain JavaScript object. You do not mutate the state. You always create a new version of it. So it's connected with what we saw before with the immutability. And also you write function that manipulate the state instead of manipulating the DOM directly. So you write function, in a sense, pure function that have no side effects. And the side effects are handled by the infrastructure, not by the application code. And the framework will update the DOM much more efficiently than you could do. And also a guideline in React is to separate UI components from logic components. So again, the logic components will be almost plain function with no side effects. Let's see it in action. So this is how you write UI component in React.js. So here I have a very simple component named square, which is just a button that receives two parameters, value and onClick. It's a button with a class, and when I'm going to click on the button, I will call the onClick function, and I will display the content of the button is going to be a value. And here is how I render the square element. So I have to call React DOM.render and then to create an element. And here I'm passing 42. I can pass 41, 43, 4, 5, whatever I want. And this is my onClick handler. And if I click here, I see that the handler has been called. And there is a way to render the component much shortly with JS6. So this is how we can render with something that looks like HTML, but it's not HTML, it's JS6. And the cool thing about JS6 is that you can mix a regular JavaScript code. So here you can, for example, have 26 plus 2, and it's 28. And again, it's click. Okay. Now let's see how we can modify the state. So now we want to have a component, the same square component, but when I click on the square, I want the state to change, and I want the value of the square to be incremented. See, and let's see how we do it. We do it by having another component, a logic component, that is going to wrap the UI component, the UI square component. This component has a state, so not only props, but props and state, while the other component had only props, properties. In the beginning, the state is going to be just a JavaScript map with value 10. And when I click the button, I will call the increment function, and the increment function is going to create a new version of the state and call setState with this new version of the state. So that's it. That is how it works. Let's restart everything. Back to 10. Here, if I want to instantiate with 1 instead of 10, I can re-render here. And 1, 2, 3, 4. So this is how you manipulate the state in React. And the guideline is not to mutate the state directly, but to create a new version of the state. Here I'm using a lambda assoc function to create a new version of the state. Okay. And Redux puts the functional programming paradigm even further and imposes even more constraints on your application with those 3 principles. So the first principle is that there is a single source of truth, the store. The state is read-only. You never manipulate the state directly. The changes to the state are made with pure function. So it seems a paradox because changes with pure function, and we saw that pure function could not have side effects. And the way it works is that you write a pure function, and the Redux framework is going to use your pure function in order to modify the state. But you, as a developer, you write a pure function. So let's see it in action. Oh, before that, once you constrain yourself to those 3 constraints, you have many positive consequences, many benefits. Your applications become really easy to test. You can track actions. You can visualize the state of the app because there is a single source of truth, the store. You can undo. Undo is just moving back to another version of the state. You can send the state over the wire to a server. You can store and retrieve the state from the local storage, and many more advantages. So let's see it's in action. It's going to be a bit complicated because Redux introduced many concepts, but I hope that you will be able to follow me. So every component, here I'm going to create a functional component using React Redux connect function. And I have to specify two things: how the state is going to be mapped to the props of. So first I have to specify what is going to be the underlying UI component. Here in our case, it's going to be square. And then I have to say how the state is going to be translated into the store. So I have to map the state to properties, and I have also to map the action to properties. So this is map state to props and map dispatch to props. Map dispatch to props will create an on-click props that is going to be passed to square. And when on-click is going to be called, I will dispatch an action called increment square value that is going to be defined below. And the state, so I have my single source of truth, the store, and I'm going to take the state square value, and this is going to be the value that will be passed to the square UI component. And this is my action. So action is pure function. I just need to translate the function call into an action type, and in this case there is no value to the action because it's just a matter of incrementing the value. And then I have a reducer that will receive the action and return the new version of the state according to the action that needs to be applied. So in our case, if I encounter this action, I want to, as we did before, to associate the state, the value key of the state, with the incremented value. And then I have to somehow combine those reducers into Redux. This is a small detail. Here is how I create the store from my reducer. And here is my app. I just need to wrap it into a React Redux provider. And as you can see, it's a completely functioning app as before. So in this case, because I have only a single component, it's not required to have a Redux application for such a simple component, but I just wanted to convey the idea behind the Redux. And one thing I'd like to show you is that I am able, first of all, to see the state. So this is my state, and if I click here, the state will be modified. This is one thing. Another thing that I can do is to dispatch an action from outside the UI completely. And let's see what happens when I dispatch the increment square value action. Oh, you see? Here, 16 has been incremented. Let's do it again. 18, 19. So I'm able to interact with my UI in a complete functional way just by calling the function. And this is also a great benefit of Redux. I think we are pretty much done. I wanted to briefly mention that functional programming is really popular on the backend also, where you have many web frameworks with Ruby, Node.js, Enclosure, and Scala. And it's much more convenient to write a web server with those lightweight languages instead of having to deal with a lot of boilerplate code with a regular object-oriented language like Java or C++. Also, some functional languages provide dynamic types like Ruby, Enclosure, and Node.js. So when you have to manipulate data, it's really simple to manipulate maps and arrays without having to deal with the types of the element of the maps and the arrays. But sometimes, sometimes you need to leverage the Java ecosystem. You want to have, for example, to use a Mongo driver that is already implemented in Java, and you don't want to rewrite your own driver. That's not a problem, and that's the rationale behind all those functional languages that have that are compiled to Java bytecode, like Scala and Enclosure, and they also provide a way for interacting with the hosting language with Java in that case. And also, I'd like to briefly mention that for big data, it's very, very popular to use a functional programming language because you want something that is really lightweight, that allows you to manipulate JSON-like data. You want to combine function, you want immutable function, you want something that is stateless. And that's the reason why there are so many popular big data frameworks that are written on top of functional programming language and then provide an API in a functional programming language, for example, Spark in Scala, Storm that provides a closure API, and Onyx also that provides a closure that is 100% closure. If you want to learn more about functional programming, or we are not that, I just presented the basics, but obviously there is more to learn about functional programming. In functional programming, we really embrace unit testing, generative testing. In some functional programming language, like Lisp, there is macro, there is homoiconicity, meaning that the code syntax is the same as the data syntax. We have pattern matching, tackle recursion. You can Google all those terms and learn more about them. Also, I put here a couple of pointers if you want to go further. This book is really the Bible of functional programming. This is my personal blog with many interesting insights into functional programming. This is an article introducing the Y Combinator that I wrote about the Y Combinator that explains how to write recursive function in lambda calculus. This is the original McCarthy paper about Lisp. And this is pointed about Redux, React.js, Closure, and one really nice talk by the author of Closure about the value of values. So I'm done. I really enjoy to be there, to spend to have spent this hour for you, with you and for you. If you need to go further with functional programming, I'm available on Codementor. You can schedule a one-on-one session with me. I'd be happy to help. If you have a question now, you can ask in the chat. And if nothing comes, I'm going to wrap up.